here we have another surface, and in this case we have the cylinder, x squared plus y squared equals 9, and here z is between 0 and 5. And we have a vector field that's in this 3D space. So we want to find this flux pointing outward. Okay, so let's graph the cylinder first. And you can see that the cylinder is x squared plus y squared equals 9 from 0 to 5. So starting as z equals 0, going all the way to z equals 5. Oh god, that's bad. Okay. So you got the cylinder. And now what we want to do is we want to find the flux that's going outward from this particular region. So you can have, again, all of our vector fields, whatever's going on in here. You have this solid in there. Now it's not quite a solid because there's not a cap. You're not really capping these with 0 and 5. So you're just looking at just the cylinder itself with no top or bottom. So, so how would you go ahead and go about this? So this problem actually, I believe it's in your notes. So, and I don't think we got to it. So how would we solve this? Well, notice that we have a cylinder. Our S is now going to be our cylinder, x squared plus y squared equals 9. So what we have to do is we have to parameterize the cylinder. And to parameterize the cylinder, well, we're going to have to use polar cylindrical coordinates. So we're going to let x equal r cosine theta, which in this case is 3 cosine theta, y equals 3 sine theta, and z equals z. So you can see that r of theta comma z, which is our parametric equation, our vector equation, is 3 cosine theta, 3 sine theta, and then z. Okay, now how do you find the flux when something is like this? So notice that we can't find the flux the same way that we did in the previous problem, because this is not a simple parametrization. It's not one of the basic ones. So how do we go ahead and go about this? Well, in order to find the flux in this type of form, so to find the flux of the surface of the vector dotted with the normal vectors, okay, over ds, in order to find that flux, well, we need to use this other formula, the double integral over the region D of the vector field. And what we're going to plug in there is going to be this parameterization, which is theta with z. And then we're going to take it with the dot product of the cross product of r theta cross with rz dA. So notice the similarities with the scalar fields with the vector fields. Now there's one thing that you have to be very careful with, because here it doesn't tell you what order you should do it, because if you flip them around you're going to get a negative cross product. So here outward, whenever you find this cross product, make sure that you check a vector. Check, plug in a point, make sure that the vector itself, the normal vector, is pointing in the outward direction. If not, and if it's pointing in the inside direction, just multiply it by a negative and you're good. The other one, we didn't have to check it because we were taking the magnitude of it, and the magnitude would just make everything positive. But in this case, you do have to check. Okay, so we have to do that, but first let's go ahead and take this cross product. Okay, so I'm going to take r partial with theta and then r partial with z. So let's go ahead and take the cross product. So first we're going to look at theta. We're going to look at every single component. So take the derivative. So this is going to give me negative 3 sine theta, and then 3 cosine theta, and then 0, because the last one doesn't have a theta. And then the bottom one, no theta, and 1 with respect to z. So now we're looking at z. You can see this guy doesn't have a z. This guy doesn't have a z, so those are going to go to 0, and then this one's just going to be a 1. So all I'm left with is just 3 cosine theta I hat plus 3 cosine theta j hat. So you can just do this one on your own, since we've done the cross product many times. Okay, this is what you end up getting. No k component, because notice if I cross out the k part, you only have this guy, which is going to go to 0. Okay, so pretty much, if I think about my cross product, you get 3 cosine theta, 3 sine theta, and 0. So here is where you want to check. So check. Is it outward? Okay, so one way that you can do is that you can just plug in maybe, I don't know, 0. If you plug in 0 in here, like theta equals 0. Okay, if you plug in theta equals 0, all you're just going to get is just, when you plug it 0 in there, you're going to get 1 and 0 and 0. Notice that it's pointing outward because this is 1, 0, 0. Is this way. It's pointing in the outward direction. So at theta equals 0, right, you're going to get an outward point. Now, if you got an inward point, to fix it, you don't have to do the cross product again. Just multiply this guy by a negative. So this one's good. Okay, so now all we really got to do is not to find the flux, is just take the dot product. So flux, okay, is going to be equal to the double integral over the region D. Oh, not S. And then F, so now we're going to look at F. So F, you can see, is going to be 2x, 2y, and 2z. That's my force field. 2x, 2y, 2z. Now remember, I know what x and y is. We figured those guys out with parametric equations. So it's going to be 2f, or 2x, which is 2 times 3 cosine theta, 2y, which is 2 times 3 sine theta, and then 2z. Well, z is just z, so it's just going to stay there. So this is the force field. This guy is my force, my F. That guy is this guy. Ooh, let me just write it like this. That guy is that guy. And now my other guy, which is going to be my cross product, I'm going to put it in here. My cross product is going to be this vector that I just found out, not the checking point. 3 cosine theta, 3 sine theta, and then 0. Okay, all over dA. All right, so this is going to give me the double integral over the region D. So you can see that I'm going to take the cross product. This guy is going to give me a 6 and a 6. So when I multiply it, I get an 18. So I get 18 cosine squared theta plus 18 sine squared theta. The last component is just 0, so it just goes to 0. So all I'm left with, well, sine squared theta and cosine squared theta, that's just going to go to 1. So all I have is the double integral of 18 dA. Oh, wonderful. Okay, so now we got to think about the region itself. So now let's go back to our picture. So it's just a cylinder. So a cylinder is just a circle. So it's just going to be whatever the radius was. The radius in this case, well, let's see. We're looking at z going from 0 all the way to 5. So it's going from a circle. So this circle itself is going from a radius. Oh, no, not from the radius, because in this case it's the theta dz. Okay, so this guy is just going to be the double integral over the region D. But in this case, because we did z and theta, it's going to be 18 d theta dz. Okay, no polar at all. Okay, I was lost. So no polar, because my only two variables are just going to be whatever the parametric equation was, which was theta and z. So you can see that in the cylinder, theta is going from 0 to 2 pi. Okay, so theta goes from 0 to 2 pi. And then the z component, if you look at the cylinder, is only going from z equals 0 all the way to z equals 5. That was given to us. So my z component is going to be from 0 to 5. Okay, so you're just going to end up getting 18 times 2 pi times 5. That's what you're going to end up basically getting, which just gives me 180 pi as my flux. Okay, and that would be my answer.